I probably just said I probably need to either explain what or why you should care about characteristic P, or what does that even mean. So, it's a recurring theme in my math life, though. So I felt obliged, if I was going to talk to this seminar, that I should do something modular. Some of the characters will come up as I talk, and maybe I should just get started. So as in a huge number of algebra talks, and probably maybe not so many other talks, but all algebra talks, by telling me that this is a field, and then I have to worry about how happy people are with having a field play a role. So the complex numbers is a field, the real numbers are a field, the rational numbers are a field. You can add, multiply, and divide by non-zero things, and multiplication is commutative. So I want to talk about vector spaces over a field. Linear algebra works in general, but I am largely interested in having the characteristic be positive, and examples of positive characteristic fields are the finite field having p elements, where p is a prime number, field having 31 elements, or a square of a prime, or an algebraically closed field. So there's some hocus-pocusy construction of an algebraic closure of any field. If you do that with a finite field, you don't get anything too mysterious. It's a theorem in Math 262, whatever it is that we teach. That I teach sometimes, that if you just take the union of all finite fields of a given characteristic, you will get a field, and it will be algebraically closed. So that's a way to construct at least one. But there are lots of characteristic P fields that are bigger than that one. So for example, take the polynomial ring with finite field coefficients, and then take the field of fractions of that, the field of rational functions with those coefficients. That's a field. It's not at all algebraically closed, but you can take an algebraic closure and you get something that's quite large. So there are lots of these. Now, that doesn't answer the question of why you care about them, but it does say something. So I want to talk about Lie algebras over K. So a Lie algebra is some kind of vector space with extra gadgetry attached to it. So one way that they arise is maybe the classical way from Sophus Lie. Probably not the way she actually would have said it, but we'll say it this way just because it's the nice way to do it. If you have a real or a complex Lie group, so what does that mean? It's a differentiable manifold that is a group, or some kind of nice manifold, maybe an analytic manifold that is a group, and all the group operations are morphisms of manifolds, so they're smooth or C infinity or whatever it is that you guys use as the language. So if you have such a thing, you can look at the tangent space anywhere, and you can look at, say, invariant vector fields, or you could just look at the tangent space at the identity, which amounts to the same thing because you have a way of translating from point to point. And the tangent space at the identity inherits a structure of some kind of algebra. Do something with tangent vectors at the identity, take their bracket, as you call it. It reflects in some way the multiplication of the group. It's a linear approximation to the multiplication of the group. So that point of view, everything that I just said works for any K. You just have to change what you mean by differentiable manifold and Lie group. So, and I'll mumble something about that. But so I tend to call my Lie algebras by this letter, G. It doesn't really look like, especially like a G. So, and I want it to be finite dimensional Lie algebra over K. So finite dimensional means that as a vector space, as the tangent space of the identity of some finite dimensional manifold, it would be a finite dimensional vector space. Like, this is not a strange hypothesis. This is the kind of thing that you're naturally led to. So let's look at some examples rather than me defining what this thing is. Because you have to listen to me talk axiomatically, which is always boring in your algebra is axiomatically. So if I take an associative algebra, finite dimensional. So and then I'll say even more example-ish. A could be n by n matrices over K. Or even better, from my point of view, I hate coordinates, the K endomorphisms of some vector space V, which is actually the same thing. So I'll just take a vector space, a finite dimension over K, and I look at all linear maps from V to V. If I choose a basis, I can identify that with n-by-n matrices. Maybe I want to choose a basis, but maybe you and I disagree on what basis we want, so we'll do this. But that is an associative algebra. I can compose linear transformations and I get another one. Yeah? Given an associative algebra, I can define the bracket of two elements. When I'm thinking about them as Lie algebras, I'm compelled to capitalize my elements for some reason. I guess because they're tangent vector fields or something. The bracket of two elements will be, I'll just take the commutator. Is that what it's called? This. Right. So I have an associative algebra, so I know how to multiply. Then I just multiply in both orders and subtract. I don't remember which order I did first. So that gives me an operation on such an associative algebra, and in particular I get one here that more or less defines what I mean by a Lie algebra. So I'm going to not. So it satisfies some identities. For example, the bracket of x with itself is 0, so that's an axiom for a Lie algebra. And the bracket of x and y is minus the bracket of y and x. And then there's some more complicated stuff having to do with the fact that a Lie algebra is no longer associative. So what associative means is that when I write products down, I can get confused about where I put my parentheses without cheating anyone. But if, in the Lie algebra, if I start nesting bracket operations, there's some identities that control it. Forgetting the name of this Jacobi identity. But it's not true that that I can do willy-nilly stuff. I have to pay attention to what the identity tells me. So it's not the same as that's what I started with. So far that's a boring list. So here is another example. If I take beta, it's actually not really important to be non-degenerate bilinear symmetric form on V. So what's that mean? Beta is a function from V cross V to K that's additive in each variable. And scalars move around the way that you expect them to, so this is an inner product. If I have V and R, or V a real vector space, an example of this would be an inner product. So non-degenerate means that no vector is orthogonal to all of V, if you like. The linear function on V defined by an element of V using this rule is never identically 0 unless the original element is 0. Anyway, it's algebraic gadgetry, and using this I can define, I guess I'll call it, I didn't really think about a good name, I'll call it GV beta. So what this really is the orthogonal Lie algebra, or the symplectic Lie algebra, depending on, no. I said symmetric, so it's the orthogonal Lie algebra, the special one, if you like. So this is it's the set of all So actually, I should have said, when A is in KV, so in matrices, I get G equal A with this bracket, with this operation, like this and that, and we write GLV for this. So it's just in my matrices, but we're reminding ourselves by writing in this stupid font that it's the other. Right. So here I'm writing in the same stupid font, but I have some extra data. I have GLV, but I'm not writing the L. I'm just telling you. It's this, and what is it? So this is, the X is in GLV, so apparently I'm producing a subalgebra, so this is, algebraics are notorious for this because I don't want to have to check. Whatever, the Jacobi identity, I want that to be for free because I knew it was true for n-by-n matrices. I don't have to bother to check gross stuff like that. It's not what I want to spend my time doing. But what I want to happen is that X should play nice with beta. And in fact, really what I want is I want a group that plays nice with beta. I should think about what I mean for the orthogonal Lie group. And it's it's angle preserving and distance preserving transformations. So it's things that if I apply the element of the group to vectors and take inner products, that doesn't change uniformly. But I need to differentiate that, because I should be looking at tangent vectors. And when I differentiate the rule that says that I leave beta invariant as a group, I get a differentiated version of that. And what it says is that I just look at all the linear transformations that preserve beta in this differentiated way. So I thought about talking about a derivation of that, but I think maybe I won't do that. So that's something that you may have seen come up if you study Lie groups, but it makes sense in this general algebraic setting. And this defines something that you can check is closed under the bracket operation. So I had already a bracket on GLV, and on the other hand, this thing doesn't come from an associative algebra. The product of two matrices in here probably doesn't have that property, but the bracket of two matrices does. That's the point. Questions? So that is supposed to point to the following thing, which I won't be as explicit about as I wish I would, because this is what I really do. If G is an algebraic group over K, so it's an algebraic group. Here's a way to think about it is the analog of this thing is the general linear group of V. So the set of all invertible linear transformations from V to V. So invertible matrices. That thing is, so how do I define when a matrix is invertible? Its determinant needs to be not zero. What kind of function is the determinant? Well, it's a polynomial function in the coordinates of matrices. So the G is therefore sort of an open subvariety defined by the non-vanishing of a polynomial function in some affine space, a space of n by n matrices or linear transformations for V to itself. And I can look at subgroups of it that are defined by polynomial conditions. So such a subgroup would be defined by conditions having to do with beta that I was mumbling about a while ago, preserving beta. So this is an algebraic group. I can so G is a subgroup of some GLV, the set of all invertible linear transformations from V to itself, is defined as, well, maybe I shouldn't say defined, is the set of common zeros of some polynomials. Scare quotes around polynomial functions from GLV to K. So actually I have to worry about what I mean by, I don't really mean polynomial, I mean something called a regular function, because I can divide by the determinant. So I need to allow myself to do that. That doesn't really change things so much. But that's what I mean by an algebraic group. So e.g., the special orthogonal group is the set of all G in GLV such that beta GV, GW is beta VW for all VW and V. That's actually the orthogonal group. Erase the S. And that is a groupy condition. If I take G and H in there and ask, does GH live in there? Well, then yes. If I do this condition once, then I can pull the G out and I can pull the H out. So it clearly gives me a subgroup. Now, on the other hand, if I write this down in coordinates, if I write down beta as a matrix, a symmetric matrix, and then I ask myself, what does it mean to preserve beta in this sense? I get a lot of equations, but they're all polynomial. They're not very complicated equations in the coefficients of matrices. So this is a closed, it's defined as the zero set of some polynomial conditions which are encoded in this shorthanded way of saying what they are. So that is a closed subgroup, and the Lie algebra, whatever I mean by that. So I will think about it as the tangent space at the identity, and then you have to worry about what I mean by tangent space. And I'm not going to say too much more than I'm not going to say too much about it. It's a little bit more of a tangent, hard than I want to go on, but it's analogous to what you would do for Lie groups. The Lie algebra that I would associate to this is exactly that GL, or G of V beta that we defined earlier. So the derivative of this condition is this condition, and it defines the Lie algebra structure of the tangent space. So we can calculate the vector space dimension of this, of the set of X that satisfy this. These are linear conditions here. Somehow, these are kind of quadratic conditions because G appears in both terms. But these are linear, or this beta is bilinear, and X only appears in one half or the other half. So this is a linear condition and defines a linear subspace of GLV. And I can compute its dimension. And that dimension is what I mean by the dimension as an algebraic variety of O of V in some sense. What I mean, there's other definitions, but it coincides with what I should mean by the definition of the dimension of that algebraic variety. Okay, so that's maybe some starting point for why I would care about the algebras. Now let me say just a few things out loud, and then I'm going to tell you that that's not what I wanted to talk about the representations of Lie algebras. I'm trying to tell you what a Lie algebra is. So here's how they arise. So why would I care about algebraic groups? So here's the big reason, is that you probably believe that people care about finite groups, even if you don't personally. It was a big theorem in the previous century, I guess, the classification of finite simple groups. So finite simple groups include the alternating groups for n greater than or equal to 5. Which you all learned that A5 was simple Math 215 or something like that. Or AN was simple for n greater than or equal to 5. There are other simple simple finite groups, ZP, the cyclic group of order P. But if I want non-abelian ones, there are also a lot, but not as many as it could be. And most of them, whatever most means, so discounting the alternating groups and discounting some oddball things that get called sporadic, which are supposedly finite in number, most finite simple groups come from looking at algebraic groups and somehow looking at their points. So algebraic groups are matrix groups, so they're subgroups of matrices in some sense. Most finite simple groups come by looking at the points in finite fields of matrix groups, of certain sorts of matrix groups. And most has to be taken with a grain of salt, or 3 or 4 grains of salt. But anyway, in some very real sense, you mainly construct the list of finite simple groups from characteristic P algebraic groups. So that's maybe my attempt to say why one cares about doing this sort of group theory / geometry / whatever in the world it is. Well, in the end, you actually get something that to worry about myself is thinking about algebraic groups with some extra adjectives that we won't mumble about, and structure of them. I mean, so you think about them geometrically. That's my meaning of the word geometrically, which probably doesn't coincide with other ones. What I mean by that is, well, I want to think about things like conjugacy classes and subgroups, and but I want to think about the conjugacy classes as subvarieties, or the closures of conjugacy classes as subvarieties. So there's a point of view that's associated with that that's important. So that's I guess my spiel about that. So more remarks. So now I want to consider characteristic K positive. So it's P, and it's positive, and then the algebras with a so-called P operation, which sounds worse than it is. So I want to be able to assign from G to G something. Let's see. So I'll denote it like this. So it's a map from G to G, and it assigns to a vector in Gx, well, another vector, which I write as the pth power, but I put brackets around it for reasons that I'll tell you about in just a minute. So if G is GLV, then x to the p is just the pth power of the matrix. I can take pth powers of matrices. And in fact, you might amuse yourself if you're really bored by what I'm saying, checking that this thing is closed under taking pth powers. So that's significant. That's not too bad. It's some sign game, but it's definitely not closed in general under taking squares, for example, unless p is 2. So, okay, but anyway, so I want to assume this, so this is clear that that's closed. The p power of a matrix is another matrix, so it's definitely closed into that. If G is the Lie algebra of some algebraic group, so here's what I didn't tell you. One way of sneaking up on what I mean by the Lie algebra is that I look at the regular functions on the algebraic group. This is some finitely generated algebra over K. Something like a polynomial algebra, about that size anyway. So not a finite dimensional algebra, but not too huge. And I can look at derivations of that algebra. Those derivations being some sort of linear transformation from the algebra to itself that satisfies the product rule, basically. It's Leibniz rule. And then I can look at derivations that are invariant under a natural action of the group on them. So this maybe sounds familiar from the point of view of Lie groups. I'm looking at left invariant derivations. And I can identify the Lie algebra with left invariant derivations. And what's obvious then is that if I take a p power of a derivation, I get a derivation. So this is a fact in characteristic p. It has no analog in characteristic 0 as far as I know. And I get always a p operation that corresponds to that p power map. On derivation. So if I take the p power of a left invariant derivation, the p power isn't going to break the invariant part. It's still going to be fixed under the action of the group. And some magic in characteristic p says I still get a derivation. And by the way, if I take this linear algebraic group, if I take this GLB, play this game from the complicated point of view of looking at it as invariant derivations, I will rebuild the p power map on matrices. So I will have worked hard to do something that I already knew how to do. Okay, so I'm looking at Lie algebras that have this p operation, and we call those restricted Lie algebras. Okay, so today I'm kind of doing algebra, or my goal was to do algebra. So far I haven't done it yet. Probably running out of time. But so I want to look at representations of Lie algebras. So that's ways of realizing them as matrix Lie algebras, or ways of having them act in the Lie algebra-y way, whatever that means, on vector spaces, so looking at modules. So it's something that you want to do for groups. There's a lot of reasons for wanting to do it. So for example, you might be wanting to study, let's look at a Lie group setting, you might want to study certain kinds of functions, L2 functions of some space, and you want to decompose those function spaces according to the action of the group. It's better to do this with a compact Lie group than in general. And that's not unrelated, but I don't want to get bogged down in that. But in order to do that, you'd like a list of candidate things that I would decompose it into. So I have some space of functions, and I'd like to write it, say, as a direct sum of things that I already understood. So that's what it means to do representation theory in some sense, and that's what I want to get at. But in order to do that, when you learn algebra, what you learn how to do is talk about modules for associative algebras. And Lie algebras are not associative algebras, and you can reinvent the wheel or you can not. So let's not. So I don't want to spend a lot of time on it, but I want to talk about the enveloping algebra for Lie algebra. So given G, there is a solution to a universal problem. All things are solved by universal problems according to McNinch in his algebra classes. So there exists an associative algebra, which I call U, which is U of G, which is actually, well, this G is finite dimensional. This is not at all finite dimensional. With a linear map from G to U that's universal in some sense. So what do I mean? Such that, so I'll say the formal definition, such that for all associative algebras A, given a map phi from G to A, such that phi of the bracket in G is the bracket in A, then there exists an extension phi tilde from U to A. An algebra is an homomorphism. Such that, and I won't write this, such that if I take the linear map from G to U and do phi tilde, that's just the linear map from G to A. So I guess part of what I didn't say is that this linear map satisfies the analog of this condition. Like that, when I put G into this associative algebra whose existence I'm asserting, did I say that? Yeah, there, close enough. Then it turns the bracket in G into the usual way of making a bracket in an associative algebra by taking commutators. So this algebra U is a solution to our problem. We don't want to talk about something weird that's not associative. We build some associative thingy that envelops it, and we can study that in order to do algebra.
So the enveloping algebra of OB is not just GLB, because it's going to be...
No. It's huge. So theorem, called the PBW theorem, which stands for Poincare-Birkhoff-Witt. And I think it is named that because it is due to none of Poincare-Birkhoff-Witt. Well, I actually don't know why it's called that. So if x1, x2, xr in G is a basis, so here I'm being sought, it's a K basis, a vector space basis for this vector space. So just take some random basis, then the collection of products x1 to the e of 1, x2 to the e of 2, xr to the e of r for ei greater than or equal to 0 is a K basis for so what is that saying? Why can I even make sense of this? Well, it is an algebra, and I didn't name this map, so I'm identifying the image of an x in there with its image in U. So I think about an x in the Lie algebra, and I think about x as belonging to U. So I'm kind of suppressing the fact that this map is actually injective. So I don't have a kernel. I'm suppressing lots of other stuff here. So I can identify G with a linear subspace of U, and then once I'm in U, I can take products of. I can take powers of things in X, and I can take products. I guess maybe I should have told you that in here, well, no, maybe I'll say this as a mumbly thing following this.
How are we going to define like E1, E2?
These are just non-negative integers.
So all non-negative?
All non-negative integers. So monomials give me a basis. So a fancy way of saying that is that essentially it's the same size as a polynomial ring in dimension of G variables.
So this is an infinite basis?
It's an infinite basis. It's the same size as a polynomial ring. So it has actually, the fancy thing to say, the way to prove this and the sort of right way to conceptualize it instead of getting lost in the subscripts is to realize that if I have two elements in the Lie algebra, I can look at x, y, in U. So x and y are elements in G, the Lie algebra, and I can look at x, y in U. And I can look at yx also. And yx is probably not x, y, but look at the difference. And that difference is now, it looks like it's of degree 2. But what it says somehow is that difference actually coincides with an element of degree 1, if you like. It coincides with the commutator. Right? So I have that xy minus yx is equal to xy is in G. So what it means is that mod lower order stuff, whatever that means, x and y commute. And that's in some sense why you're able to get away with this. Yeah, in general, I have an algebra which, if the bracket on G is not trivial, I have an algebra that's definitely not commutative. Yeah, xy is definitely not yx if x bracket y is not 0. Yeah? And so a priori, I should have x1, x2, x1 should not be, it should be some element that I can't sort of reconcile to this form. But this says that I can do it mod lower order stuff. And, well, I just have to do the bookkeeping right, and I found that I get a basis. So it's not saying that it's trivial to multiply these. I mean, the product of two of these monomials is not obtained just by adding the corresponding e's. Right? You get lower order crud. It can be a mess, but you do get a basis. So that's what the PBW theorem says. So what's special about characteristic P, I can now say. So I think this is a little bit. So recall we have x to the p is in G for x in G. So we have a p power operation, right? I'm putting myself in the situation. I mean, there are probably V algebras that don't have that, and I don't care about them. I don't know anything about them. So it's not so interesting from my point of view. And on the other hand, I can view x as an element of U, and in U I can take its 13th power and its 411th power and its p power. Yeah, and x to the p is in U. And it's probably not that guy. In fact, it's definitely not. No reason why it should be. This says that it's definitely not, right? Because x to the p is one of these monomials. Well, okay, if I take it as a basis element, sorry, in general, I don't have to worry about it. But if I take x as one of these basis elements and I take its pth power, then I can write it as a linear combination of basis elements. So stuff with ei is equal to 1 only. And on the other hand, this x to the p is one of these things with e1 equal to p or e whatever, some exponent of p. So they're definitely different things. So in fact, so I'm not going to prove this. I'll mumble something about why it's true. But this is this that x to the p minus x to the p. So it's a difference of very different elements is in. Sorry for the notation. It's in the center. Right? We spell center with a z. It's a z. E, okay. So dumb German joke. It's in the center of. It's in the center of the developing algebra. And in fact. I don't think that you will be too surprised because they're both supposed to act. Somehow they're both of these elements act the same way. I'll say something about representations in just a minute. The point is that both of these elements act the same way on all kinds of representations, which makes it be central. And moreover, the elements x1 to the p minus x1 to the p have a fixed basis, yeah? Well, pretend like I fixed this outside this theorem statement. So there's a basis of G. This element, x r to the p, I should do it in the same order, are, what's the word that, algebraically independent. So they're in the center, which is a commutative algebra, right? If I'm in the center, I commute with everybody. In particular, I commute with everybody else in the center. So the center is a commutative K algebra. And these are algebraically independent over K. So what does that mean? They act as if they were polynomial variables. Or I can view them as polynomial variables. So we get a subalgebra, Z0, which is the subalgebra generated by these things, x1 to the p minus x1 to the p, xr to the p minus xr to the p, contained in Z, contained in U. And this thing is a polynomial algebra in R variables. I mean, they're kind of funny-looking variables, but they're just, I just view them as variables. I could give them new names and quit worrying about writing in brackets and p's and stuff. Yeah? And the PBW theory even tells me more. It tells me that U, I mean, it's big, but it's not so much bigger than this thing. So let's say that precisely. Moreover, U is a free Z0 module. Free. So now I have some oddness that maybe I have to worry about which side I view as a module on. the statement is true. The statement that I'll make is true in both cases, but I may as well fix ideas so that we'll get ahead of it. So why is it a module? Whenever I have a subalgebra of another algebra, I can multiply every element of U by an element of Z0, and surely all my module axioms. So I can view this thing as something that I can multiply by scalars in Z0. So it's a free Z0 module. So what's free mean? I should have a basis, and I should have, you know, spanning and linear independent statements. And I have to worry a little bit more about what I mean when I talk about fields, but not that much. It's essentially the same definition. So every element of U can be spanned by some given basis, which I'll tell you, and any expression in that basis is unique. So on a basis, so I take my given basis of x, x1 to the e1, xr to e, did I have parenthesis or something? I did. And now what's the point? Is that more or less I get z0 by taking p powers. Okay, I have some difference, but it sort of doesn't hurt me in the quotients that I have to look at. So here I take so I just don't want them to be any bigger than p, because once I get to p, I've sort of accounted for stuff here. So the rank as a Z0 module of U is P to the dim G. Its rank reflects the dimension, the vector space dimension of the vector space, but it also reflects the prime P, which is, you know, this is just not even close to anything that is vaguely true in characteristic 0. There's nothing like that for the Lie algebra, for the enveloping algebra of the Lie algebra. It has a center, say for a reductive Lie algebra. Let me tell you what that means. If it came from a compact Lie group, there's some corresponding complex Lie group. There has a Lie algebra, which is on a nice list. It's classified in Harish-Chandra, proves some theorem that exactly describes the center, and it's much smaller than this. I mean, this thing is huge. I mean, it accounts for most of the enveloping algebra, which is a remarkable fact. So what I have failed to say very well is associated with just introducing the enveloping algebra. So I want to look at representations of a Lie algebra. So those are Lie algebra homomorphisms from G to GLV. Gasp. I should wish I didn't have to think about Lie algebra homomorphisms, but that's defined by this property, basically. So I want to look at maps from my Lie algebra into the general linear Lie algebra of a vector space V, and I want it to play nice with the bracket in this sense. So what this says is that that's the same thing as asking for modules for the enveloping algebra. Just look at the ordinary module as you open thumb and foot and see what a module is. So it's an abelian group with an action of the ring that you're looking at. So that's exactly why you cook this thing up. It's an associative algebra whose modules are just exactly the representations of your Lie algebra. So it gets you out of even having to define what you mean by the representation of the Lie algebra. It's just a module for the enveloping algebra. So the theorem that I want to formulate, now, good thing I have notes. Where am I? Right. Theorem. Okay, now I have to use another word. Use the word and then talk about it. Each simple G module is finite dimensional. And if E is a simple G module, in fact, its dimension is less than or equal to E. This is spectacularly not true in characteristic 0. So there are infinite dimensional simple modules. Simple. So what's simple mean? So a G module is the same thing as a module for the enveloping algebra, and to say that it's simple means that it only has a boring list of submodules. There's the 0 submodule, and it has the everything submodule, and then it has no intermediate guys. So those are the only submodules. Sort of like being a prime number. Only these divisors. Yeah. So I have so I'm starting with a simple G module, and that's often what one wants to classify. So in nice situations, one knows that every module is a sum of simple modules. That's spectacularly not true in our setting, but I'll hide that. It is true for finite dimensional modules for a Lie algebra characteristic 0, for example, but it's not at all. Undimensional modules for a nice enough Lie algebra characteristic 0. Sorry. It's not true. Yeah, I definitely need the nice enough. Anyway, so I want to talk about simple modules because they're kind of constituents. Kind of like talking about simple groups. There's a hard problem for describing an arbitrary group in terms of a simple group, but okay. So we look at a simple G module, and in characteristic 0, you have lists of the simple modules for, say, the special linear or the general linear. The others and their dimensions can go out to infinity, and there can even be infinite dimensionals. And this says that the dimensions of simple G modules are bounded by something bounded, not by something that grows, but by something that is determined by the field and the Lie algebra. Not any bigger than that. And this is actually this is just a fact that's a ring theoretic and some module theoretic. So more generally, that A non-commutative algebra, Z not containing a central subalgebra. So I'm thinking of A as being U, non-commutative algebra over K. So this is a central K subalgebra. I want to suppose that Z0 is finitely generated over K. So for example, it's a polynomial ring, this setting, and that A is a finitely generated Z0 module. So that's weaker than what we're assuming. We're assuming it's not only finitely generated, they're even free. I don't really care about the free. Then, in each simple A module is finite dimensional over K. Do I torture you by proving this like this? So we are in this setting. So I have exactly this situation, and this is just a general fact. So I take. Indeed, I'll scribble for a little bit, and then I'll look and see that you're all wishing that you had had more pizza. Then, if E is a simple A module, note that E is equal to AX for any. Actually, I'll just do this one. If I take a non-zero element of E, I can just generate a submodule. Look at the cyclic submodule generated by A. A is a unital ring, so this cyclic submodule contains X, which is not 0. So AX is not 0. And E is simple, so AX is E. So what that says is that somehow that, oh right, sorry, I'm going to get off into what I wanted to say. So that says that that E is generated by a single element, and now write A as Z0. Well, sorry. Let U1 to UT be Z0 module generators for A. So A is a finitely generated Z0 module, so I just take some generators. Then E is the sum of Z0 UIX. So it's a finitely generated Z0 module. And now I need to make it be fun. I mean, somehow I have to see why it's finite dimensional. So this is the hocus pocusy part. Note that Z0 is Noetherian. It's a finitely generated K algebra. So E contains a maximal Z0 submodule E prime. So it's probably not a submodule, but a maximal submodule. And then E mod E prime is isomorphic to Z mod Z0 mod some maximal ideal. Because that's a maximal submodule, it's just the same thing as saying that E mod E prime is a simple submodule. go through this, just point out the dictionary between some ring theoretic language and module theoretic language. E mod E prime is a simple Z0 module. Simple Z0 modules look like this. And now the point is that that I see that M, well, to conclude, M annihilates E. So I'm skipping a little bit, just because I want to torture you more. But basically what that means is that E is really a Z0 mod M module. Z0 mod M is a field extension of K that's finite dimensional because it's finitely generated. So this is a finite dimensional K vector space. I would have made my life a little bit simpler by supposing that K is algebraically closed, but it's not that much different. So you kind of see the mechanics of stuff that goes into this, which is a lot of algebra. But in the end, I find, well, I didn't tell you about this bound, but I'm not surprised by that. So this, I think, requires K bar. I may have some trouble with it. No, I don't. Never mind. This is okay. So that I will try to sneak the other results in. But what it says is that in some sense you don't have so many simple modules, and it says something else that I haven't emphasized, and I want to conclude by pointing that out. And that is that I can look at a linear space, more or less. I mean, this thing is the ring of polynomial functions and some tweak of the Lie algebra itself, some kind of p-power version of it. Right. It's the ring of polynomials in our function, in our variables, but in a natural way, it has something to do with the p-power of the Lie algebra, whatever I mean by the p-power. And what one finds from this sort of point of view, by finding this maximal ideal M, it corresponds to a point in whatever Z0 corresponds to. Z0 is some functions, and I have a maximal ideal in some functions, and it corresponds to a point in the corresponding algebraic variety, if you like. And that point is important. So it gives you an organizing principle for telling simple modules apart. So to a simple module, I associate a point in this geometric gadget, and yeah, so there's some remarkable theorems. So about 10 years ago, in the 1970s, however many years that makes it, Katz and Weisbeiler made a conjecture about a more precise version of estimating the dimensions of E. So they had a particular kind of Lie algebra. They had some more geometry going on, and they worked algebraically closed fields. So this M was a really maximal ideal with quotient equal to K. And what they said is they looked at the elements of this geometric space that corresponded to that maximal ideal, and they had noticed that the corresponding algebraic group acted on this geometric space. So you could look at its orbit. And that orbit always had even dimension. So it had some dimension, which was even. And what they proved is that if E was a simple module corresponding to M in this way, that P to half the dimension of that orbit divided the dimension of E. So they've got a lower bound for E. So this is a remarkable fact. This says that E can't be too big, but on the other hand, if there's some geometric input about here that says that E can't be too small if the geometric input is interesting, if its orbit is large, for example. The last thing that I'll say is the thing that I suppressed is the most interesting case from where I came from mathematically is the opposite extreme, when the orbit is really small and the orbit is somehow the zero element of here. Because those are the Lie algebra representations that you get by differentiating the representations for the group. That's what you really wish you understood. And so somehow Katz and Weisbeiler's theorem tells you almost nothing. It says that one divides the order, the dimension of those. But the idea somehow was to try to use some sort of deformationist argument, to understand the big ones, because there are fewer of them, because they're big, somehow, and deform down and understand these pesky ones that are, that are hard to get your hands on. It's work in progress. So actually describing the dimensions for a nice group of the simple Lie algebra representations, which account for some of the simple group representations, is solved for P bigger than some unknown bound, but it's not solved anymore. There's quite a lot of work to be done. Anyway, thanks for listening.